Today's comic panel is to help you be able to use triboelectric in a sentence. You ever wonder about the first person to discover the triboelectric effect? Everyone, I've been rolling around in dead cats, and now I can shoot tiny lightning bolts from my fingers. If you look smack in the middle of your study guide, pages 8 and 9, Field Days. We are actually going to start on the right-hand side, which is more dedicated to electric fields. If you glance at the bottom of page 8, fields are much more than just a useful tool or model. Fields are real physical entities which store and transfer energy. This is something you're going to look at a bit today and a little bit more closely as the rest of the days play out of this study guide. So on page 9, what is the SI unit of charge? What we're asking by this is how much charge is built up on an object. So you take the balloon, rub it against your head, you build up a charge in that balloon, and we want to be able to measure how much buildup of charge is on that balloon. Scientists who spent a fair amount of time investigating the interaction of charges, such as electrons interacting with other electrons, electrons interacting with protons, is the individual from France, Charles-Augustin de Coulomb. So the SI unit of charge is the Coulomb, and the symbol is a capital C, capital C. So up here you have capital C for a Coulomb. Now when we were looking at SI unit for length, width, height, amplitude, it's the meter. We're able to show you here's what 1 meter looks like. And if we break a meter into the various parts, you can use those prefixes, centi, hecto, kilo, to give you how much of a meter you have. Now you can do the same thing with the prefixes with coulombs, but it's a little less easy to show you here's 1 coulomb. And this leads us to letter I of how is the SI unit of charge defined. It's not something I can say, look, here in my hand is 1 coulomb of charge. We won't be able to say, show me 1 coulomb, as you did with show me 1 meter. So the coulomb is defined as the charge of 6 24/100ths of a billion electrons. Now, it's important to distinguish the charge of. We're not saying that 1 coulomb is equal to 6 quadrillion electrons, but to the charge, the energy of 6 24/100ths billion electrons. And here's certainly where our scientific notation is coming into play and helping us here. 6 24/100ths times 10 to the 18th. This, for historical reasons, is kind of a throwback as to how Coulomb defined various other factors associated with charge, especially movement of charge. We're in this study guide dealing with just static electricity, electrostatics, often called as in the basic law of electrostatics. And static electricity is the buildup of charge on an object. You're not having that energy transfer from one object to other. Now you will, when you scuff your feet across the carpet, you have a static discharge, but we're not being able to take this static electricity and use it to run off any electric equipment that requires an outlet, plug it in, so on and so forth. So very important to establish that the Coulomb is defined as the amount of charge of 6 quadrillion electrons. If you take that out of scientific notation, that's the number you'd have to be writing all the time and possibly doing calculations with. Give you some information so you're up to date in the world of science. As of the 20th of May 2019, the elementary charge of the proton, is exactly that number. That is an incredible amount of accuracy. That is a very, very detailed, accurate, with lots of accepted values or targets on the measuring equipment. So the Coulomb is exactly the charge of 1 1/6 times 10 to the negative 19th protons, which is about this 6 24/100ths times 10 to the 18 protons. Now remember, an electron has the same magnitude but opposite sign of charge of the proton. The information being conveyed in this sentence is similar to the way you would look at the basic atomic model, where you have a nucleus that has your neutrons, neutrally or no charge, your positively charged protons, and then in your electron cloud, if you have hydrogen, 1 proton, and electron would be 1, that would be a negative charge. So we're saying that they have opposite sign or charge. So minus, positive, negative, positive, those are opposite signs. But they have the same magnitude, meaning they have the same strength or amount of charge. That the amount of charge on the electron is the same as the amount of charge that a proton has. They're just oppositely charged. So magnitude is the strength, or how much, how many of something. If the cross-country run is a 5K, the magnitude of the cross-country run is 5. The how many, how much kilometers, 5. So the amount of charge electron and proton are the same, just the opposite signs for the charge. Now, through all that, what you need to remember is how the SI unit of charge is defined, what it means. And that's this right here, that the charge of 1 Coulomb is equal to the amount of charge of 6 billion electrons. That's the key thing to remember. 1 Coulomb is the equivalent of 6 and 2400 billion electron charges. What does the SI prefix nano mean? Well, nano means a billionth, 1 billionth. If I chop a meter stick into 1 billion even pieces, one of those pieces is the billionth of a meter. We'd call it the nanometer. And we have 3 short videos. The first 2 kind of help you enter the nano world, recognize just how truly small, a billionth, a millionth even, so small. And then the third video is looking at the nanoscale of how we've been able to capture image of atoms.
What is nano? Nano is a unit for measuring the extremely small. Nano size is measured in nanometers, which is 1 billionth of a meter. How much is a billion? For example, let's look at an emperor penguin. Let's zoom in on the emperor penguin's skin. This tick is about 1/1000th of a meter. The bacterium attached to the tick is about 1/1,000,000th of a meter. And there is the bacterium's DNA. The DNA's radius is about 1/1,000,000th of a meter. That is 1 nanometer. DNA is made up of many atoms, and atoms make up all matter. This is the nano world. This nearly invisible world can be viewed with an atomic force microscope.
Feel free to have a bake sale to purchase us an atomic force microscope.
Have you ever seen an atom? Seeing as everything's made of them, you have, but have you ever seen one on its own? Over time, microscopes have become more and more powerful, allowing us to see deeper into the world of the ultra-small. Traditional light microscopes can be used to see things like these onion cells and the structures within them as they divide, pulling apart their chromosomes. But scientists have come up with a whole host of clever methods to observe far smaller things. Using beams of electrons instead of light, we can generate detailed images of chromosomes themselves. Recently, groups of scientists around the world are becoming able to see materials at the most fundamental scale, the atomic. One group from the University of California in Los Angeles have been getting up close and personal with nanoparticles of platinum, just a few nanometers across. Each of the tiny dots you can see here are actually individual platinum atoms. But researchers didn't stop at a two-dimensional picture. By imaging over 100 slices of the nanoparticle at different angles, then removing the noise with a special filter, they were able to map the location of almost every atom. The information was used to create a three-dimensional reconstruction of the whole particle in unprecedented detail. It may look blurry, but this particle is estimated to contain over 27,000 atoms, and so, like flies in a swarm, they appear to merge together. Every so often, though, we see the platinum's atomic structure align, granting us a moment of clarity. This technique is being used to analyze tiny irregularities in the structure of the particle called dislocations. Dislocations are subtle, like the misalignment of the green and red layers of atoms in this particle. But nonetheless, they can significantly change the properties of materials, with effects ranging from a change in the efficiency of LEDs to the strength of metal alloys. Three-dimensional atomic-scale imaging like this is bettering our understanding of the structure of materials on this truly fundamental scale.
So a little look into the nano world, or much more than a little, tiny look into the nano world. We have ourselves the question, how much of a Coulomb is a little n capital C? Well, the capital C is our SI unit of charge. The C doesn't actually stand for charge, it's Coulomb, the unit itself. And then your metric prefix of a little n, that is the nano Coulomb. So how much of a Coulomb is a nano Coulomb? Well, it's 1/1000th of a Coulomb. 1/1000th of a Coulomb. 1 nanocoulomb is 1/1000th. So there's your millionth, billionth of a Coulomb. And this amount is represented in scientific notation, a billionth, as 10 to the negative 9. The final unit we'll need to look at today for you to embark on this activity is the volt. The volt is the SI unit of push. You have to have a difference in electrical pressure in order for electric charge energy to flow in current electricity. So if you have a 110 outlet, you know it's 110 volts. And when you plug something in, you're not paying the electric company for electrons to flow through the electrical wiring. You're paying for them to push that initial electron. If you remember way back at the beginning of physics, we mentioned to you that everything in physics is about that physics wave, that oscillation back and forth. You have equilibrium and you oscillate about equilibrium. In the world of electricity, when we're talking about plugging things in, that's current electricity rather than static electricity or electrostatics. So, as I said before, you're not paying the electric company to send you electricity so that you're able to plug something in. Wow, that's an outlet. And say, okay, feed me electrons. When you have a plug, glad I don't have to draw a European or UK plug here. When you have a plug going to, say, a lamp, because we all have triangle lamp shades, let's connect the wire to the lamp. When you plug this into the outlet, those electrons are already there. Remember, atoms make up everything, and atoms have electrons. So you have an electron next to an electron, billions upon billions, trillions, quadrillions of electrons that make up this wire. When you plug it in, you're having the electric company provide the initial push. So that if I have an electron, if I push this one, so the energy coming from the outlet, and I push on that first electron, it's going to cause repulsion, this oscillation, this back and forth, this wave motion. That, remember, the fundamental principle of waves is that they transfer energy and they don't transmit matter. So this electron with this atom doesn't end up over here into the light bulb. The energy is transferred. So you often hear people say the flow of electrons is electricity or current electricity. It's actually the flow of the charge or the energy of those electrons. So that long spiel. What is a volt? A volt is the SI unit for electric push. That kind of kick that the electric company provides that you pay for. They're not sending electrons to you. All of those already exist in all the electronics and objects that are in the cosmos. We're just paying for, give us a little push to start that mutual repulsion, and that energy is transferred. So what's a volt? SI unit of electric push. And it is named after Alessandro Giuseppe Antonio Anastasio Volta. The unit is volt or volts. The symbol is a capital V. And just to make you a little bit more smarticle, we don't actually have the term udge in the metric system. The amperage, wattage, voltage tend to be US American additions. For example, you wouldn't say what would be the volume of the swimming pool. You wouldn't say 1,000 literage. You wouldn't ask the distance of the field and say it's 500 meterage. The udge seems to be added to electrical terms when it should just be volts. So now I'm not taking away saying the sign isn't dangerous. Yes, it absolutely is dangerous. The sign would probably be more effective if it was this one of not only will this kill you, it will hurt you the whole time you're dying. But really we should be talking in terms of volts or the volt. All right, we're going to need to know these units because you're going to be looking at field strength, volts per meter, how much electrical push per a certain distance in meters. And the potential, that's another way to think of the volt, electric potential, the potential to push that energy repulsion of the electrons. So you're going to use the online FET charges and fields simulation to investigate how test charges interact when placed in an electric field. And we'll show you that website. So with your Chromebooks, you'll obviously go to Chrome, type in FET and charges and fields. You shouldn't have to download. You can simply press play. And that's really what we want you to do, is kind of play around with our electric field. So you want to make sure your electric field is showing. So if I were to put a billionth of a Coulomb of charge into this electric field, the charge as it moves, you can see how the electric field responds. Now remember, the field is the force around that right here positive proton, the energy field around the proton, and these arrows are just representing those field lines. They're modeling the electric field lines. You can bring in an electron, and you can see the classic repulsion, or excuse me, the attraction field. I believe we can put 2 in here, remove that one, and now you can see the repulsion field, that void area right here. So in your study guide, the first row, we are asked in the first column of the first row, the test charge distance. So let's put the classic electron there. And our test charge, our sensor here, and we want it to be 1 meter away. So Put center there. Stretch out 100 centimeters, as that is the 1 meter equivalent. And we'll call that good. And then I put my charge right here. And the first column wants to know the field strength. Well, let's actually jump to the third column, the potential at location. So here's the location. That's right, here's the voltmeter. So I can put that right here, and this is my equipotential. Potential is that push, the potential energy, if you will, the potential to put energy in the repulsion of those electrons. So we could call that -9 volts, and -9 just meaning in this direction, kind of like a number line to the left of 0. And then the middle column, the field strength, that is volts per meter. That's actually done for you, where you can click values, and it tells you right there. You don't have to worry about the degrees. But you have 9 9/10 of a volt per meter. To work on the rest of the table on page 9 of your study guide, you quite literally just play around, move your charges, and if you want to be very attentive, you can add grid lines. And then if you want to just refresh the whole page and start over, there's a refresh down here. Once you have filled out the table, you can go back to the PhET simulations. Actually, it's sometimes faster just to type in here, and you're going to do PhET electric hockey. And it's this electric field hockey that you're going to play, powered by Chirpy J instead of Adobe Flash. So this will be the electric field hockey game you play for field days. Here's the puck. You can change the puck to negative if you like. We'll keep it as a positive. Speaking of positives, you can pull out positives here. You can think of them as players, defenders, pop down a few electrons. Of course, the goal is to score a goal. So this is just practice. Hit start. Oh, so basic law of electrostatics. I created these electric field lines of positive, which cause that electron puck to go out of the field of view. You can reset. You can clear. And let's see here. So I want some attraction to... Does it show repulsive? Yeah. So this is just like the test charge that was in your previous simulation. And let's just drive it right into the goal. Let's see if I can score. Start. Gotta love the validation. And you can increase the difficulty level where we have a barrier in place here. So you've got to consider how to move around that barrier. Let's just take a look at difficulty level 3. Magnificent. So your task is to complete the chart in the middle of page 9 of your study guide. And then you can play around with some electric field hockey. So let the games begin.